Welcome to your deep dive on black holes. We've got a fascinating set of notes here. Looks like excerpts from a Spanish language course, all about black holes, relativity, gravitational waves, the works. Someone's been brushing up on their astrophysics, but no worries, we're diving deep, gonna break it all down, from the very first theories to the mind-blowing stuff we know today.
Yeah, absolutely. We're going to try to untangle some of the mysteries surrounding these cosmic enigmas that really challenge our understanding of the universe.
You know, it's funny, when I was looking through this, what really struck me was how some of the earliest ideas about black holes, I mean, way before Einstein, we're talking 1700s, it's like they kind of had an inkling.
It is remarkable, yeah. You had thinkers like John Michell, Pierre, Laplace, working with Newton's law of gravity, right? They were already speculating about objects so massive, so dense, that light itself couldn't escape their pull.
Wow.
The idea that gravity affects light, they took that and ran with it, envisioning these, they got dark stars. Dark stars, huh? Makes you wonder what they would thought of what we know now. I mean, especially once Einstein came along and kind of shook things up.
Yeah.
So how did his theories, how did they change how we think about gravity and black holes?
See, Einstein's theory of general relativity, that was a game changer. Instead of gravity being this force, he described it as a curvature of space-time caused by mass and energy. Picture this. Imagine space-time is like a giant trampoline.
Okay.
And a bowling ball. That's your massive object, like a star.
I'm picturing it. So the bowling ball, it would make like a dip in the trampoline, right?
Exactly. Massive objects, they create these what we call gravitational wells in the fabric of space-time. And this warping, this bending, that's what dictates the movement of everything around it, planets, even light itself. So it's not so much a force pulling things down, it's more like space-time telling things how to move. Whoa, that's incredible. Like the universe is saying, hey, you're not in control here, space-time is. So this warping, this warping that you're talking about, this is directly leading to a black hole forming.
It's a key ingredient. Think about stars, but much, much more massive than our sun. They live fast, they die young, and when they exhaust their fuel, they collapse. And I mean collapse under their own gravity. This creates incredibly dense remnants.
Okay, so you've got these massive stars collapsing. So
Okay.
where does the black hole come into play?
This is where it gets really, really interesting. Depending on the initial mass of the star, this collapse, it can form a neutron star, which, fascinating on its own. But for those stars massive enough, that collapse, it doesn't stop. They keep collapsing, becoming so incredibly dense that nothing, not even light, can escape the gravitational pull. That's your black hole.
So it's like the ultimate recipe for cosmic drama, right? Take a giant star, let it burn out. If it's massive enough, boom, you get a black hole. But what happens then? Once something or someone, I don't know, crosses that point of no return, the event horizon.
Now that's where things get truly strange. Just imagine, you could observe a black hole up close, which in itself, right, mind-bending.
Yeah.
As you get closer to this event horizon, time itself, it actually starts to slow down for you.
Wait, hold on. Time slows down. Like,
Yeah.
I would actually age slower than someone back here on Earth.
You got it. It's called time dilation, one of the most bizarre consequences of extreme gravity. The closer you get to a black hole, the slower time runs for you relative to someone further away. Now, at the event horizon itself, from the perspective of someone observing, you would appear frozen in time, forever hovering at the edge of this black hole.
So I'm frozen in time at the edge of oblivion. But what about my experience? What would I actually see happening?
Let's just say it wouldn't be a pleasant experience.
So it's like we're looking for the shadow, right? The imprint of the black hole's influence on everything around it.
Precisely. And another amazing tool we have, another tool in our Cosmic Detective Kit, is the detection of gravitational waves.
Ooh, okay.
Remember our trampoline analogy?
Yeah, the bowling ball and the trampoline warping space-time.
Now imagine you dropped another bowling ball on that trampoline. What would happen?
It would create, like, ripples, right? Like waves spreading out from where the two bowling balls collide.
Exactly. When incredibly massive objects like black holes, when they collide, they cause these ripples, these waves in space-time. These are gravitational waves, and they travel across the universe at the speed of light.
So we're actually detecting waves in the fabric of space-time itself. That's incredible.
It's pretty wild. And you know what? In 2015, scientists using these incredibly precise instruments, LIGO and Virgo, they made the first ever detection of gravitational waves. And these were from two colliding black holes. This This discovery, it confirmed like this key part of Einstein's theory, and it opened up this whole new window into the universe.
It's like we can listen in on the universe's biggest, most energetic events now. You also mentioned different types of black holes, and we've talked about, the ones that form from dying stars. But then there's this whole other breed, the supermassive ones. So what's the deal with those?
Supermassive black holes, these are in a whole other league.
Hmm.
Stellar mass black holes, they form from individual stars, but supermassive black holes, millions, even billions of times the mass of our sun.
Oh, whoa, hold on. Billions. Billions of times the mass of the sun. It's almost too big to even picture.
It is truly mind-boggling.
Yeah.
And these behemoths, they're found at the centers of galaxies, including, you know it, our own Milky Way.
Wait, so you're saying there's a supermassive black hole right in the middle of our galaxy. So all the stars, our sun, everything, we're all just swirling around this giant, I don't even know what to call it.
It's a humbling thought, isn't it? And these supermassive black holes, they're not just sitting there. They actually play a crucial role in the formation and evolution of galaxies. They're like these cosmic architects influencing the movements of stars and gas on a galactic scale.
Okay, so we've got the stellar mass black holes from dying stars, these supermassive ones shaping galaxies. Are there any other kinds of black holes out there?
There's this theoretical possibility, and I say theoretical, of primordial black holes. The thought is these would have formed in the very early universe, like moments after the Big Bang. These hypothetical objects, they could range in size from incredibly small to as massive as a mountain, potentially.
Primordial black holes. So we're talking like looking back to the very beginning of the universe, but this research you picked out, it had something that I really wasn't expecting. So we've been talking about this intense gravity of black holes, how they warp time and space, but to think that they might not last forever, that's a twist I wasn't expecting.
It really challenges this idea we have of black holes, right? Like these cosmic vacuum cleaners where nothing escapes.
That's exactly what I thought. So what could possibly destroy a black hole?
Well, it's not so much about destruction as evaporation.
Evaporation.
You see, Stephen Hawking, back in 1974, he proposed this idea that black holes, they're not entirely black. They actually radiate a tiny bit of energy, a phenomenon we now call Hawking radiation.
Hold on. Black holes they're giving off energy. But how is that even possible? I thought their whole deal was that their gravity is so strong, nothing, not even light, can escape.
Right, and that's where things get really interesting. We have to dive into the world of quantum mechanics.
Okay.
See, in the quantum realm, empty space, it's not actually empty. It's buzzing with these things called virtual particles, constantly popping in and out of existence.
Okay, I think you just lost me. Virtual particles.
Think of them as pairs of particles, but with opposite energies, constantly appearing, disappearing, annihilating each other in a vacuum. Now, near a black hole's event horizon, things get a little weird.
Weird seems to be a common theme with black holes. So what happens near the event horizon with these virtual particles?
Sometimes one of these particles might fall into the black hole, while its partner, it escapes out into space. And that escaping particle, it carries away a little bit of energy from the black hole.
So it's like the black hole is slowly leaking energy, kind of like a dripping faucet over time.
That's actually a great analogy. This energy loss, this Hawking radiation, it causes the black hole to very, very, very gradually lose mass. Yeah. And eventually, over ridiculously long timescales, it could evaporate entirely.
Black holes evaporating. It's like they're vanishing into thin air. You've blown my mind today. But before I spiral into an existential crisis about the impermanence of even the most powerful things in the universe, is there anything else we need to hit on about black holes? Because this is incredible.
There's one more really wild thing about black holes we should talk about. We've gone on and on about how they warp time and space, but all that distortion, it does some pretty incredible things to how we even see light itself.
Okay, yeah, we did kind of breeze past that.
Remember those gravitational waves, the ripples in space-time from those massive collisions?
Oh yeah, that was huge.
So picture this. Those ripples, they're passing through space, right? And as a gravitational wave, it stretches and squeezes space-time. It actually stretches and squeezes the light that's traveling through that same space.
Right, really? So those waves, they can actually warp the light itself. It's like they're leaving their mark on everything.
That's a great way to put it. And this warping, this distortion, it can cause something called gravitational lensing. Basically, light from really, really distant objects, we're talking galaxies billions of light years away, that light gets bent, magnified by the gravity of something massive like a black hole that's between us and that distant object.
So it's like the black hole is this giant magnifying glass just floating out in space, distorting and making the light from behind it look bigger.
Exactly. And for astronomers, this gravitational lensing, it's like this amazing tool. We can use it to study the early universe, even map out dark matter, which, it doesn't give off light itself, but it still has gravity.
It's like getting a glimpse back in time to the universe's baby pictures or something.
Something like that.
We started off with those early ideas centuries ago, and now we're talking about using black holes as tools to figure out the mysteries of the universe. It's incredible how far our understanding has come.
It really is remarkable, isn't it? Human curiosity, this drive to understand the universe around us.
Yeah.
And what we've learned about black holes, curved space-time, time dilation, Hawking radiation, gravitational lensing, it's revolutionized how we see the cosmos.
It really has. This whole deep dive, it's been quite the ride. I mean, we started with bowling balls and trampolines, and now my brain's trying to wrap itself around black holes evaporating over eons. You've given me a whole new perspective on these things, and honestly, a whole lot more to think about when it comes to the universe.
And that's what's so exciting, right? It seems like with every answer we find, we're left with even bigger, even deeper questions. How do those supermassive black holes even form in the first place? What role do they play in how the universe evolves? What happens to information that falls into a black hole? These are questions that'll keep scientists and anyone who looks up at the stars wondering for a long time to come.
It's humbling and incredibly exciting all at the same time to think we're just starting to scratch the surface of understanding these cosmic enigmas. And on that note, we'll leave you with this. If black holes are ultimately defined by their gravity, what happens when gravity itself maybe meets its match? Something to ponder as you continue your own exploration of the universe. Thanks for joining us on this incredible deep dive.